So in this video, we're looking at AQA's 3.1.9 topic, rate equations, which builds on the kinetics topic that featured earlier in the course. So measuring any rate is measuring how quickly something changes. So one rate of change that we are very familiar with is speed. The information that speed is giving us is it's telling us the rate of change, the rate that our distance is changing per unit time. So typically speed is measured in meters per second, and so speed is telling us how many meters we are changing by, or something is changing by, per second per unit time. Now in chemistry, the rate of a reaction is the measure of how fast the reactants are converted into products. We might be focusing on the reactants, or we might be focusing on the products, but we're examining sort of a rate of change. A key thing to establish whenever thinking about rates is that all rates are proportional to 1 over time. This is a fundamental point. So everything you do about rates is going to be proportional to 1 over time, to something over time. You're going to be measuring the change of something over time. In chemistry, this is typically the change in concentration. Now in the topic 3.1.5, kinetics, we considered the factors that could affect the rate of a reaction along with why this was through referring to collision theory. So these were the 5 factors that we considered. So with temperature, if we increase the temperature, then we increase the energy of the particles along with the frequency of collisions. And so overall that led to an increase in the frequency of successful collisions. In the case of concentration, if we increased the concentration, this increased the frequency of successful collisions. Pressure, increasing the pressure increased the frequency of successful collisions. Catalysts, while using a catalyst results in a lower activation energy and therefore a greater proportion of successful collisions. We saw that most markedly, or we sort of could see that more clearly when we did the Maxwell-Boltzmann curves. And then finally, surface area. So increasing the surface area increased the frequency of successful collisions. So the rate was a measure of how many successful collisions were happening per unit time. Now, up until this point, we have only considered the rate of reactions in a qualitative sense. So I can say if I increase the temperature, I increase the rate, but I have no real sense of by how much. I can say if I increase the concentration, I increase the rate, but I have no sense of by how much. So we've only considered the rate of reactions at GCSE and in year 12 or in the 3.1.5 kinetics topic in a qualitative sense. However, it's possible to collect data during the course of a reaction that allows us to plot a graph, which can then provide us with quantitative information regarding the rate of reaction. So if we double the concentration, do we double the rate of reaction, or do we quadruple it? Or is there another factor it increases by? So there are various methods we can use to collect data during a reaction, and the one that we choose to use will depend on the reaction itself. So we'll choose the method most appropriate for that particular reaction. Now, if we're collecting data throughout a reaction or during the course of the reaction, then this is called continuous monitoring. So we are continuously collecting data. And so one example where we could do this is if there was a gas produced. So in this reaction here, we have calcium carbonate reacting with hydrochloric acid, and that produces salt, water, and carbon dioxide. So one of the products is a gas. We would see fizzing or effervescence, and we could measure the volume or the mass of that gas produced over time. So if we wish to measure the volume of gas produced during the course of the reaction, then one thing that we could use is a gas syringe. Apologies here for the quality of my diagram. So as the reaction proceeds, the syringe fills with gas. We can measure the volume every however many seconds, 10, 15, 20, whatever it is. And so what we can see is we are essentially continuously monitoring the reaction. We are continuously collecting data throughout the course of the reaction. We're measuring the rate, essentially or we're going to be able to use that information to measure the rate at which one of the products is produced during the course of the reaction. Another option is to measure the change in mass during the course of the reaction. So as the reaction proceeds, carbon dioxide is able to escape. We've got the cotton wool there. Because when there's effervescence and bubbling, it can actually sort of spit out some of the solution. So it prevents the loss of the solution, but doesn't stop the loss of the carbon dioxide. And so what we can measure as the mass changes is the mass of the carbon dioxide that's lost during the course of the reaction. So that's another way to continuously monitor, to continuously collect data during the course of a reaction if one of the products is a gas. Now, when you look at this reaction here, one of the things to notice is we do have a gas being produced actually, but one of the products is a solid. And when we look at the left-hand side, both of the reactants are solutions, and they would actually be colourless solutions. But when you have a precipitate, so when a solid is formed out of solution, one of the way that you will most likely recognise that is that the solution goes cloudy. So if a solution goes cloudy, that means you've got a precipitate. Equally, you could have a change in colour. So you could have, for example, a zinc reacting with copper sulfate, and copper sulfate is a blue solution. And during the course of the reaction, as the copper 2+ ions were reduced to copper metal, then what you would see is you would see that blue colour fade, and so you could sort of monitor it that way. So if you have a precipitate or there's a change in colour, then what you can use is something called a colorimeter. What a colorimeter does is it measures the absorbance of light. So we could measure the absorbance of light in our reaction mixture every however many seconds, 10, 15, 20, and so on. So in the reaction here, as the precipitate is formed, the absorbance of light increases. In the case of a change of colour, like the example with copper sulfate, then what you've got is that the absorbance is proportional to concentration, and the actual concentration at those points can be found using something called a calibration curve, which is prepared using known concentrations. This is something you'll come across when you do the transition metals topic. But essentially, a colorimeter in these examples is allowing us to follow the course of a reaction and measure its rate. A final method for seeing the change in rate through continuous monitoring is measuring the change in concentration of a reactant or a product. And you can do that, and of course it does depend on the reaction, but you can do this, one method is by titration. So you could do a titration at specific times during the reaction. Now the problem with this method is that just because you take the sample out to titrate doesn't mean that the reaction stops. So let's say you're deciding to do a titration every 30 seconds. Maybe that's a little bit optimistic, but let's just say for every 30 seconds. When you take the sample out at 30 seconds and you're preparing your titration or beginning your titration, the reaction is still proceeding, even in your sort of sample conical flask or vial or whatever. So this only works if the samples are quenched. So quenched is a key word, and what we mean by quenched is that the reaction is in effect stopped. So if you're going to measure the change in concentration of a reactant or product and you're doing it by a method such as titration, then you need to quench the reaction, or you need to quench the reaction in your sample the moment that you take your sample. Now, if there's an acid catalyst, so if in the reaction mixture there's an acid catalyst and that's not what you're measuring, then what you can do is you can neutralize that acid, so basically remove the catalyst, and that in effect, it doesn't stop the reaction, but it slows it down massively. And then another possibility is to place the sample in an ice bath. So you're reducing the temperature, and that would dramatically slow the rate of reaction. Or another alternative is to dilute the mixture. So if you dilute the mixture, you're dramatically decreasing the concentration, so hopefully in effect stopping the reaction. but you're not changing the number of moles. And if you remember that what you're doing in a titration is you're measuring the number of moles. So you would be measuring the number of moles in each sample, and that would allow you to see how the reaction had proceeded. That would be your continuous monitoring. So just to go back over that, so if one main method for measuring the changing concentration of a reactant or product would be a titration, assuming there is a suitable titration. When you take your samples, you must quench them, which means that you must, in effect, stop the reaction in those samples, so that when you take the sample at 30 seconds, that is, you stop it at 30 seconds, so that you know that is what was there after 30 seconds. If it's an acid catalyst, you can do that by neutralizing the acid, so therefore removing the catalyst, or you can place it in an ice bath, lowering the temperature, dramatically reducing the rate of reaction, not perfectly stopping it, but in effect stopping it. And finally, you could dilute the reaction mixture. If you dilute the reaction mixture, you massively decrease the concentration. You hopefully, in effect, stop the rate of the reaction, or stop the reaction. But what you don't do is, or what you're not doing, is changing the number of moles, and that's what you're measuring. That's what you're doing the titration against. So here's an example reaction regarding measuring the changing concentration of a reactant or product. So we have our bromoethane reacting with our hydroxide ions. So this is a nucleophilic substitution reaction. And we could take samples every however many seconds or minutes. And then in this particular example, we would quench it either by using an ice bath or by diluting it so that the reaction was in effect stopped. And then we could titrate using an acid to measure the number of moles of hydroxide ions in the sample. And then we could use that to determine the concentration of hydroxide ions at the time the sample was quenched. And that would be a way of continuously monitoring a reaction such as this one. Now, once we have our data from any of those methods that we've just looked at, then we can plot a graph. And then the gradient at any point on that graph will give us the rate of the reaction at that point. So if the graph is a curve, and they usually are, then what we do, or what we need to do, is to draw a tangent to the curve at that point. And a tangent is a line that touches a curve at only one point. So here are two examples. So the one on the left is perhaps the gas syringe example, where the volume of gas produced was measured over time. And so the gradient here would tell us the rate of change in volume of gas at that particular moment in time, for that particular tangent, sorry. And then the one on the right, that could be, say, the concentration of hydroxide ions in the nucleophilic substitution reaction. So the gradient at any point on the curve would tell us the rate of the reaction at that particular moment in time during the course of the reaction. So you do, drawing tangents is absolutely a part of this topic, and there are exam questions or questions in exam papers which require you to draw tangents, or to draw a tangent, and to measure the rate of reaction at that particular point in time. Now, the tangent can be anywhere on the curve, and when you're sort of practicing, you might be drawing a number of tangents, but that's something that you need to be prepared for, and it's something that you need to be comfortable in doing. Now, if we draw a tangent when the time is equal to 0, so right at the start of the reaction, then this would give us the initial rate of the reaction. So this brings us to the point now where we have data, and I said at the beginning of this topic that in the past you'd only ever looked at rates of reaction in a qualitative sense, and that now we were going to be looking at it in a quantitative sense. And so that brings us now to the general rate equation, which is the main focus of this topic. So there's a general rate equation given here. Rate equals K, and then the concentration of A to the power of M and the concentration of B to the power of N. So rate is obviously the rate of the reaction, but its units are critical, and they are moles per decimeter cubed per second. K is the rate constant, so it's a constant of proportionality, and its units depend on the rest of the rate equations, so they are essentially to be confirmed. So we're going to look at that separately. So K is the rate constant, and its units depend on the rest of the rate equation. Concentration is represented using square brackets. So if you have a substance with square brackets around it, then what that is saying is it's the concentration of that substance. So we have the concentration of A here, and of course concentration is measured in moles per decimeter cubed. Now M and N in this general rate equation, they refer to the orders of reaction with respect to the reactants A in the case of M and B in the case of N. We'll understand a little bit better what that means in a second, but for the moment those raised powers are called the orders of reaction, and they are the order of reaction with respect to whatever the concentration they are associated with. So M here is associated with A, so M is the order of reaction with respect to A. If we add M and N together, then what we get is the overall order of the reaction. So looking at the orders of reaction, at A level there are only three that you can need to concern yourself with, and they are zero order, first order, and second order. And as you can see, what we mean by saying zero order is that it's the concentration raised to the power of 0, first order the concentration raised to the power of 1, and second order concentration raised to the power of 2. So what they are providing us, what we're now able to see is how changing the concentration would affect the rate. So if we consider A, if we change the concentration of A and it was 0 order or first order or second order, we could see how that affected the rate of the reaction. Now if we start with 0 order, anything raised to the power of 0 is 1. So what that means here is if I double the concentration, I will still have a value of 1, because if I raise anything to the power of 0, it's 1. So for the first time, we are discovering that it might be possible that concentration does not affect the rate of reaction. In the past, at GCSE and in kinetics in year 12, we've always said increasing concentration increases the rate of reaction. We've always said that concentration affects the rate of reaction. That may not always be the case. So if we discover that a reaction is 0 order with respect to a particular reactant, then changing the concentration of that reactant will not affect, or does not affect, the rate of the reaction. So moving on to first order, we have the concentration raised to the power of 1, which means it is just still the concentration. What this would tell us in the rate equation is if we doubled the concentration, then we would double the rate of the reaction. If we tripled the concentration, we would triple the rate of reaction, and so on. Finally, we have second order. So we have the concentration of squared. So we have here the concentration of A squared. So that is the equivalent, or that is the same as saying A times A. And so what we discover here is that if we say double the concentration of the reactant, then what would actually happen to the rate is that it would be quadrupled. It would be 2 squared, right? So if we double the concentration, we quadruple the rate of reaction. So it's whatever the change in concentration is squared, that's the effect it would have on the rate of the reaction. So we're just going to see an example. This is a possible reaction. It's an ionic equation for a reaction. And it's determined experimentally that the rate equation for this reaction is rate equals K, and then the bromate ion to the power of 1, but as it's to the power of 1, we don't show the 1. Bromide ion also to the power of 1, and H plus ion also to the power of 1. So What we're deducing here is that the orders of the reaction with respect to all three reactants are first order, and that the overall order of reaction is 3, or third order. So as I mentioned a little while ago, the units for the rate constant depend on the rate equation. So if we take the rate equation that we had on the previous slide and rearrange it so that its subject is K, then the way we now work out the units of K are exactly the same as the way we did it for Kc. So we know that the units of rate are moles per decimeter cubed per second, and we know that the units of concentration are moles per decimeter cubed, and so this allows us to work out the actual final units. So it's a question of cancelling out what we can, and then resolving what we have left. Now, what you never do is leave units as a fraction. So our final answer here is moles to the -2, decimeters to the 6, and seconds to the -1. So they are our units of K for this particular reaction. So crucially, rate equations can only be determined by experiment. And the initial rates method is one way of doing this, and it involves collecting and analysing experimental data. So the initial rate of a reaction is the rate of the reaction at the moment the reactants are first mixed. So we would be drawing a tangent at t equals 0, for example, and that would give us the rate at the beginning of the reaction. The reaction can then be repeated with different concentrations, and then the different time taken is recorded. So the concentration of one of the reactants is changed. The concentration of all the other reactants is kept constant. So this is just like this is a fair test. We change one variable, that's our independent variable. We keep everything else the same. They are our control variables, and then we measure something. In this case, we measure an outcome in the reaction, and then by comparing the results, we can form or deduce a rate equation. So we're going to consider how we might determine the rate equation for, say, this reaction that we have in front of us. Now, this is an example of an iodine clock reaction, and the iodate ions react with sulfite ions in the presence of an acid. Now, the reaction can be followed by using starch solution to detect the formation of iodine, and it's called a clock reaction because the colourless solution turns black very suddenly after a certain length of time, and it's the time that's measured, and it's the time that provides us with information on the initial rate of reaction. What in effect we're doing is we're measuring how long it takes for the reaction to reach a certain point. So it's a little bit like an analogy would be a 100-meter race. We can time how long it takes for the athletes to run 100 meters. And here we're timing how long it takes for the reaction to get to the point in which the iodine turns the starch blue-black. So the illustration here is intended to illustrate sort of what's happening. So we have a colourless solution, and the reaction there'll be a sudden change. It'll go blue-black, and we're measuring the time it takes for that to happen. So here are some results. So we've got 4 different experiments. That's what the runs mean. Run 1, 2, 3, and 4 on the left. And then we have the different reactants. And we have the time it took for the blue-black colour to appear. And then, of course, rate is proportional to 1 over time. So we've then converted the time taken into a rate by doing 1 over time. Now you'll notice that there are differing volumes of the iodate ions, different volumes of the sulfite ions, and there's different volume of the acid as well. And you'll notice there's a 4th column here, which is water. Now water isn't part of the reaction, but the reason it's here and the reason that it changes, or it's a different volume in run 1 compared to 2, 3, and 4, is that if you look at the total volumes for each of the runs, they're kept the same. Now, the reason that the total volume must be kept constant in this type of reaction, or when we're collecting this data, is so that the concentration of each reactant is proportional to the volume we added. So if we added 20 centimeters cubed of sulfite ions instead of 10 centimeters cubed, because in both versions the total volume was the same, then what we have in effect done is doubled the concentration when we've gone from 10 to 20. So the total volume in each run is 50 centimeters cubed. So in run 1, 10 centimeters cubed, 10 over 50 is the proportion of sulfite ions, whereas in run 2 it's 20 over 50. So we have in effect doubled the concentration. So now what we're going to do is we're going to compare the change in concentration of one of the reactants and see how that affected the rate of reaction, and then that's going to inform or give us the information for determining the order of reaction with respect to that reactant. So we're starting by comparing runs 1 and 3 here. So if we look at the iodate ions, we have the same concentration in 1 and 3. If we look at the sulfite ions, we have the same concentration in 1 and 3. What we are changing here is the concentration of the H plus ions. So we have doubled the concentration of H plus ions in effect. Remember that the volume that we added is proportional to the concentration. What is the effect on the rate of reaction? Well, we have doubled the rate of the reaction. So we doubled the concentration of hydrogen ions and we have doubled the rate of the reaction. So this tells us that the rate is proportional to the concentration of H plus ions. And that in turn tells us that the reaction is first order with respect to H plus ions. So if we double the concentration of H plus ions, we double the rate. We triple the concentration of H plus ions, we triple the rate. We quadruple the concentration of H plus ions, we quadruple the rate. If we now look at runs 1 and 4, we are now looking at how the concentration of iodate ions affects the rate of reaction. So the change in concentration from 1 and 4 is double. So we have double the concentration. The change in rate is quadrupled. Now, it helps to see the change in rate as a factor of the change in concentration. So the concentration doubled, the rate quadrupled, but in effect what that means is it was 2 squared. So that I think that allows us to see, therefore, that the rate is proportional to the concentration of iodate ions squared. And so this in turn tells us that the reaction is second order with respect to iodate ions. So if we double the concentration, we increase the rate by a factor of 4. If we triple concentration, we increase the rate by a factor of 9. If we quadruple the concentration, we increase the rate by a factor of 16. So we finish by comparing runs 1 and 2. Here we are changing the concentration of sulfite ions. We can see that we're doubling the concentration of sulfite ions, but there is no effect on the rate of reaction. So this tells us that the order of reaction with respect to the sulfite ions is 0 order. So we can change the concentration of sulfite ions however we wish, double, triple, quadruple, and it will have no effect on the rate of reaction. And this is one of the sort of revelatory aspects of this topic, I think. Up until this topic, concentration has always, in terms of your education, affected the rate of reaction. And what we're discovering here is that isn't necessarily the case. So we put this all together and we get our, we get that the rate is proportional to the concentration of hydrogen ions to the power of 1, iodate ions to the power of 2, and sulfite ions to the power of 0. So now we can write our final rate equation. We don't include anything that is 0 order, so our final rate equation will look like this. So including K, it's a constant of proportionality, so now we have an equal sign rather than a proportional sign. We are not including the sulfite ions because they are 0 order with respect to that. So something else to notice here is that the final rate equation bears no relation to the stoichiometric equation for the reaction, i.e. the overall reaction equation. So you can never look at a reaction equation and deduce the orders of reaction with respect to each reactant. Rate equations can only be determined experimentally. That's the only way they can be determined. Okay, so we're going to have a look at another example. So I'd like you to just pause the video for a moment and have a look at the values that are given here and have a think then about how you might determine the rate equation with respect, well, to determine the orders of reaction with respect to D and E. Right, so we have to begin by comparing two of the experiments in which the concentration of only one of the reactants is changed. And in this case, that means we have to start with experiments, or we have to start by comparing experiments 2 and 3. So if we look at experiments 2 and 3, it's only the concentration of E that changes. So as we can see, when the concentration of E was doubled, the initial rate quadrupled, and that tells us straight away that the reaction is second order with respect to E. So we can partially complete our rate equation at this point. So now we know how the concentration of E affects the rate of reaction, we can compare two different experiments and determine the order with respect to D. So let's choose runs or experiments 1 and 2. Now when we look at runs 1 and 2, one of the things that we notice is that D does change, but so does E. So we're going to have to factor that in and we're going to have to refer back to our partially filled rate equation. But let's just see how each concentration and the rate is changing. So D is increasing by 1.5. So I find it more helpful to try and use fractions. So it's increased by a factor of 3/2, and E has also increased by a factor of 3/2. I think you'll hopefully see why I think it's better to use fractions in a second. If we look at the rate, and this might take a bit of thinking about, because obviously it's easy to work out as a decimal how the rate has increased, but it's actually increased by 27/8. So at this point, I'm going to use a sort of modified version of the rate equation that I've given at the top of this page. So I've got the change in rate equals the change in concentration of D to the power of M times the change in concentration of E to the power of 2. The reason it's to the power of 2 is because we've already worked out that the order of reaction with respect to E is second order. So now I'm going to substitute into that expression the changes that we've just determined. So the change in rate is 27/8, and that equals the change in the concentration of D to the power of M times the change in the concentration of E squared. So I now resolve this expression, and I can now see that M must equal 1. So the reaction is first order with respect to D. So that gives us the final overall rate equation. So rate equals K times the concentration of D times the concentration of E squared. So we return back to the first rate equation example that we saw, and we realized here that the concentration of one of the reactants doesn't affect the rate of the reaction. So as I mentioned earlier, this is a clear modification of the factors we learned at GCSE and in the kinetics topic in the AS level content. So concentration does not always affect rate. And this obviously raises the question, why not? Because collision theory is still completely relevant. So I'm going to try and explain why this is the case, why concentration doesn't always affect, by starting with an analogy. So imagine I've prepared 10 worksheets, 10 different worksheets, and I want to collect them into a complete set, and I ask for help. So initially the worksheets are arranged in 10 piles, and so Manny collects a page from each of the piles. That's step 1 here in this picture. Miala takes the set of 10 pages and tidies them ready for stapling. That's step 2. And then Matthew staples the set of notes together, step 3. Now a fourth person volunteers, and I have to think, who should I put them with so that the completed sets get made faster? Or in other words, which is the step, or which step is the one that is determining how quickly the sets are compiled? So I could add a second person to help Manny, I could add a second person to help Miela, or I could ask get the second person to help Matthew. So I want you to think about who I should put this fourth person with so that the sets of worksheets get made faster. So just pause the video, have a little think. So I hope it's obvious that step 1 in this process is the one that determines how quickly the complete sets are made. And that because that's clearly the slowest step of the 3. So I need to speed up the slowest step. That's really what I need to do if I'm to compile the complete set of worksheets faster. Now I hope you've begun to appreciate from the organic mechanisms that you've done so far that chemical reactions can take place over a series of steps, and this can be true of all inorganic reactions too. So the overall rate of a reaction, the one that you would measure if you did some experiments, is controlled or determined by the rate of the slowest step, and we call that slow step of reaction the rate determining step. Now crucially, in any mechanism, species that are only involved in steps after the rate determining step do not appear in the rate equation. So what that means is that species that appear in the steps up to and including the rate determining step will feature in the rate equation. So what I hope you're beginning to see is that we find the rate equation by experiment. We've already established that. But then we're able to use that rate equation to deduce possible mechanisms. So a substance that acts as a catalyst will appear in the rate equation, but not in the overall chemical equation for the reaction. That's because if it's a catalyst, it's not being used up, so it would appear on both sides of the equation and therefore would cancel out. That's sometimes a question at A level. They may ask you what's the role played by whatever it is, and this is where you've been given a rate equation or you've determined a rate equation. If there's a substance that is in the rate equation but it does not appear in the overall reaction equation, then its role must be a catalyst. So let's consider this reaction here. We've got propanone reacting with iodine, and we're forming iodopropanone. So the reaction is acid catalyzed, and we can use a colorimeter to follow the course of the reaction because we will get the iodine being used up, so we'll get a color change, and that enables us to work out the following rate equation. So we discover that the rate is proportional to the concentration of propanone and the concentration of the acid catalyst. So iodine does not feature in the rate equation. Well, it turns out that this reaction proceeds through 4 steps. And we can see that the first step is the slow step. So as the iodine molecules are not involved in this proposed mechanism until after the rate determining step, because remember the slow step is the rate determining step, the overall rate of the reaction would not depend on the concentration of iodine. So this is a little bit like our collecting the worksheet sets analogy, and step 1 is like Manny taking one of each worksheet and putting them together, and then steps 2 and 3 or 4 are the people who follow and whose sort of jobs could be done very quickly. So although this topic is called rate equations, and we have spent quite a long time on rate equations, another significant part of this topic concerns rate graphs. And there are 2 types that you have to be familiar with and you have to understand. The first is concentration versus time, which we've already been introduced to, but we're obviously going to talk about with respect to the 0, first and second order. And then after that, we can use those to determine rate versus concentration graphs. Now, whenever you're asked to plot something versus something, that is always y versus x. So whatever comes first is the y-axis, whatever comes second is the x-axis. So it's y versus x, so it's going to be concentration on the y-axis and time on the x-axis. And in the second one, rate versus concentration, rate is going to be on the y-axis and concentration is going to be on the x-axis. And y versus x is a general rule. So one of the things that we need to appreciate is the shape of these graphs. So if the rate of reaction was a 0 order with respect to the concentration of A, for example, then A would still be used up, but the concentration itself, it would be used up, sorry, at a constant rate. So what we would discover is that our graph was a straight line. That is supposed to be straight, apologies. If the reaction is first order with respect to A, then the shape of the graph is of the type that you've probably seen many times before at GCSE and in the kinetics. So here we can see that the rate of reaction is fastest at the beginning, and we get this curve as the concentration of A decreases. Now, this isn't something that you do at AQA, but it is something that you do in other exam boards. What you would discover if it was first order is that you would have a constant half-life in this curve, or on this curve. Anyway, that's the shape of the graph when it's first order with respect to the concentration of A. At first glance, the shape of a concentration versus time graph when it's second order with respect to the concentration of A looks the same as a first order. However, it's actually much steeper at the beginning. And so this is where the half-life method, which isn't something we do at AQA, would be useful, because you would discover that the half-life here increased. So it wasn't constant. It wasn't a constant half-life. It increased each time. Whereas first order, it is a constant half-life. Now, once we have a concentration versus time graph, one of the things that we can do is we can draw tangents at different concentrations or at different times, and we can then calculate the rate at those times or at those points in the reaction and plot a corresponding graph of rate versus concentration. So apologies that my tangents aren't terribly good here. I'm having to sort of sketch this freehand. But essentially, we are drawing tangents at different concentrations and working out the gradient of those lines. And by working out the gradient of those lines, we are working out the rate of the reaction at those concentrations, and that is now giving us the information or the data to plot a rate versus concentration graph. Now, if you remember the zero order shape for the concentration against time graph, it was a constant gradient, right? It was a straight line. It was a constant decreasing gradient. Now, if it's a constant gradient, that means the rate's constant. So that means when we're plotting this graph, we just get a straight horizontal line. That is supposed to be a straight horizontal line. Now, we can also see this mathematically if we think back to the rate equation. So if we're saying it's zero order with respect to A, then we're saying that the rate equation here is rate equals K, and then the concentration of A to the power of 0. And of course, anything raised to the power of 0 is 1. So what we're saying is that rate equals K. And one of the things that we know about K is that it's a constant. That's the whole sort of point of it. So hence we get this constant value for the rate, and hence why we get this straight horizontal line. Now, I think it is useful actually to approach the shapes of these rate versus concentration graphs using the rate equations. So if our rate is first order with respect to the concentration of A, then our rate equation is going to equal rate equals K, and then the concentration of A, and of course it's the power of 1, but we don't show the 1. And then a way of thinking about this is to just imagine easy, simple values for the concentration of A. So if A, the concentration of A was 1, then the rate would equal K. If the concentration of A was 2, then the rate would equal 2K. If the concentration of A was 3, the rate would equal 3K, and so on, and so on, and so on. So what I hope it becomes clear from this is that if the concentration of A was 0, then the rate would be 0. So that means we're going through the origin. And then we have a constant or a proportional increase. So we would get a straight line like that. And that is, that's directly proportional. and it's directly, directly part of directly proportional is because it goes through the origin. Finally, we have second order rate versus concentration graph. So again, going to use the rate equation. So our rate equals K, and then it's second order, so it's A squared. So let's imagine the concentration is 0. So that means the rate equals 0. So we know we're going through the origin again, sorry. If the concentration of A equals 1, then the rate equals 1. If the concentration of A equals 2, then the rate equals K, apologies, the rate equals 4K. If the concentration of A is 3, then the rate equals 9K. And then just to do one final one, if the concentration of A equals 4, then the rate equals 16K. So we can see a different shape here, and what we would have is something like that. Now, there was an exam question once where it was a second order, or the reaction was second order with respect to a substance, and they asked you to plot a rate against concentration squared graph. So so the way to approach this is to always think about the rate equation. So we're saying rate equals K A squared for a second order reaction. If we remove K, then we're saying that rate is proportional to A squared. Well, our axes are rate and A squared. So that means our line, if it's just simply proportional, is going to be a straight line like that. Because again, if the concentration of A is 0, then the rate will be 0. So this would be the shape of a rate versus concentration squared graph for a second order, or if the reaction was second order with respect to A. So just watch out for that. That's a way that you can be caught out. So we've been focusing on concentration and how that affects the rate of a reaction. But as we know from the Maxwell-Boltzmann, and also even from our GCSE work, from the Maxwell-Boltzmann curve, that temperature affects the rate of a reaction. And that's because we have a greater proportion of particles with energy equal to or greater than the activation energy. So now that begs the question, if this is the rate equation, where does temperature feature? Now there's only one possible place, and that is in K, in the rate constant. Now to understand how the rate constant and temperature are connected, we have to now look at something called the Arrhenius equation. So this is the Arrhenius equation. It looks really quite scary, but the thing to slightly put your mind at ease is the fact that you will always be given it in an exam if you're having to use it. So you don't have to remember this equation, although you need to be comfortable about what it's telling you and what it means. So we obviously know what K is. K is the rate constant, and its units depend on the rate equation. But of course, it will always include seconds to the -1. A is known as the pre-exponential factor. All you need to really remember is the fact that it's a constant, and its units will depend on K. E is an irrational number like pi. It features quite a lot. It features a lot in science and in maths. You just need to be familiar of it as a button on your calculator. T is temperature, capital T is temperature, remember lowercase t is time. So capital T is temperature, and the units are Kelvin. Finally, we have R, the gas constant, which you've met before, and that has the units joules per Kelvin per mole. So you can be asked to do a calculation using the Arrhenius equation. So we've just got an example question here. So the rate constant K for a reaction varies with temperature, as shown by the equation. And then they give us the Arrhenius equation. For this reaction at 25 degrees Celsius, K equals 3.46 times 10 to the minus 8 seconds to the minus 1. So they've given us the units for K. The activation energy is 96.2 kilojoules per mole, but bear in mind in the Arrhenius equation it should be in joules per mole. And the gas constant is 8.31 joules per Kelvin per mole. You're always going to be given the gas constant. So calculate a value for the Arrhenius constant A for this reaction and give the units for A. So first thing that we need to do is to turn the temperature into Kelvin. So that is 273 plus 25, so equals 298. So you do need to watch out for unit conversion. And then the activation energy needs to be in joules per mole, so that equals 96,200 joules per mole. Sorry, I just forgot to put the Kelvin, the K for Kelvin there. So now we're going to go and do the actual calculation and work out the units for A. So the first thing to do is to rearrange the equation so that A is the subject. So we're going to divide both sides by e to the minus EA over RT. So that gives us A equals K over, and then it's e to the minus EA over RT. Now it's a question of substituting in the numbers. So we know that K is 3.46 times 10 to the minus 8. And then it is e to the minus, and then the activation energy was 96,200 joules per mole over the gas constant times the temperature. So one of the things that we need to do here is to resolve that on our calculator. So we're going to put that into our calculator, and that gives us a final value of 2.57 times 10 to the 9. Well, now we haven't worked out the units yet. That's our next thing to do. But it's exactly how we would have worked out the units for K, exactly how we would have worked out the units for KC. So I'm going to take the A equals and expression and put in the units. So we knew that K in this example was seconds to the minus 1. We know that it's E, well that's just a number, but it's to the minus. So this is where it's going to get a little bit messy. So we've got joules per mole, because that's the units of activation energy, over joules per Kelvin per mole, and then it's times temperature, so times Kelvin. So now we can simplify that, begin to simplify that. So the joules cancel out, the kelvins cancel out, the moles cancel out. E is just a number, so we're talking about units here. So we end up with the final unit of seconds to the minus 1. Now it's possible to determine the activation energy of a reaction from this equation by plotting a suitable graph. So you don't need to know how to do this or how this next expression is derived, but essentially if you natural log, that's ln, ln, if you natural log both sides of the equation, then you end up with the following. And if you look at this, we know we can measure rate during the course of a reaction, and rate is proportional to 1 over time, and we know that K always has as part of its unit second to the minus 1. So essentially K is proportional to 1 over time. So we can work out ln K, we can work out the rate of the reaction. That would be our dependent variable. That would be the thing that we were measuring. And then if we're talking about this expression here, then this is all to do with how temperature affects rate. So we could explore how we could change the temperature, which means that 1 over T here, 1 over the temperature, would be our independent variable. And so we can now see this expression. Sorry, it's quite convoluted, but hopefully it will now make sense. We can now see this expression in the form of y equals mx plus c. So ln k, which we've basically worked out from measuring the time it takes for something to happen by measuring the rate. X, because we've changed the temperature, so that's our independent variable. We can see that minus EA over R, well, that's going to be a constant. That's the gradient of our line. And then A was a constant, so ln A will be a constant. So we have an expression that is in the form y equals mx plus c, which means if we plot y versus x, if we plot ln k versus 1 over temperature, then the gradient of the line that results will be minus EA over R. If we calculate the gradient, multiply it by minus R, then we will get the activation energy. So we're plotting ln k, which is proportional to the rate, proportional to 1 over time, against 1 over temperature, which is Kelvin to the minus 1. When we plot this, we will get a straight line because it's of this form, y equals mx plus c. That straight line will have a negative gradient. We can see that it's got a negative gradient. We work out the gradient by doing the change in y over the change in x, and that equals m in our y equals mx plus c, and m is minus EA over R. So then we multiply both sides by minus R. So we end up with EA equals minus the gradient times R. So we'll now have a positive value because the gradient was negative. So it's negative minus negative is positive. We will get, at this point, it will be in joules per mole. So we then divide it by 1,000 to get it into kilojoules per mole. So activation energy is always a positive value. So if you end up getting a negative value, that means you've made a mistake somewhere, probably in determining the gradient. You've just done the change in y or the change in x or something the wrong way round. In fact, it'll be the change in y you've done the wrong way round. So, but this is a method for calculating the activation energy. So this can be a sort of 8-mark question in an exam. What they would do is they would have the table of results that was almost fully complete. That you would likely have to fill in 2 missing values. So you would likely have to do a ln k calculation and a 1 over temperature calculation. You need to make sure that when you fill in any table, any partially filled in table in an exam question, that you do it to the same number of significant figures / decimal places as the other data in the table. So you would do that to start with, and then they would give you a sort of piece of graph paper on the page, quite likely to have one of the axes already, the scale for one of the axes already done, quite likely to already have the 1 over temperature scale done. You would need to do an appropriate scale for ln k. You need to make sure that when you draw your line that it's occupying at least 2/3 of the sort of area, as it were, of the paper. And then you would work out the gradient, and then from the gradient you would be remembering, you would be given this equation, by the way, and you need to remember that minus EA over R is the gradient, and you could then work out the activation energy from there. And it would be in total about 8 marks. So that concludes the rate equations topic. I hope that has all made sense, but if you've got any questions, please just leave a comment. Thanks very much.